Alright, time for another draftphysics.com, debatephysics.com. But again, the debate is very broken and not subject oriented. There's no argument, counter argument, at least nothing rationally connected to the arguments. Bunch of misparaphrases and distortions and perversions. So anyway, there is this issue to be argued about the nature of gravity and what kind of force it is. Okay, so this part of the video might be just because it's, you can only use analogies. There's no other way to explain what something is except to explain what it's like. Alright, so they won't provide any description of anything they think gravity is like. So I can't do much with their side of this. And I'm simply stating that it seems like, okay, what you're basically saying is you could have an area of space, okay, just any old space. And let's take the atmosphere out of it and all the other mush and just say that we're going to go from a point A in that space to a point B in that space. And that's the objective. And so let's just say the space was filled with just little dots. Okay, so they're little randomly placed, randomized little dots, and they don't do anything except just be little dots. And you could argue that what we're really trying to measure is how much energy do we have to use to get to point A to point B going through this field of dots. All right, and the simple truth would be, if they're not moving, okay, they're just stationary, that I could pick some path, and there'll be a path that'll get me from point A to point B, hitting the fewest dots. All right, but let's say we can only go in straight lines. Okay, we're a rocket ship, and I can't really do a whole bunch of navigating or any of that kind of stuff. We can just pick a path and go straight. So it goes straight, and let's just say if we did that 100 times, the average number of dots it hits is 5. Okay, so that's what it takes to get from point A to point B. Is you have to incur the penalty, okay, of hitting 5 dots, and the 5 dots cost you whatever, some fuel, okay, some amount of fuel. So you don't use any fuel until you hit a dot. Okay, you could argue, and so this is what it's going to cost you: 5 fuels to get from point A to point B. And it's really not going to matter how fast you do it, right? Because it's not moving. It's not a constant thing or anything like that. It's just a dead force. It's just dead. All right, so now let's change the scenario and understand that the dots, the impediments, the counter stuff, now there's going to be gravity, essentially, is what I'm saying. See, there's no gravity when they're not moving. They're not pushing down, so there's no gravity. And now the simple argument is I'm going to simulate gravity by just having those dots move down. And that'll essentially simulate gravity, where I'm going to get hit with 5 dots. So let's say now we have the dots, and then we're going to say per second, we're going to just per second put another 5 in here. So there's 5. Okay, you're going to hit a number. You're going to hit 5, and we're going to double that now. Per second, we're going to add another 5. So for every second, there's 5 dots hitting you. So now you have to use 5 fuels, okay, when you're just sitting on the ground, because there's 5 dots hitting you. Okay, so the dots are moving down now. Now they're little down dots, okay, and you're refilling the dot atmosphere constantly. There's more dots coming in at a rate of this, let's say there was 100 in here when it's stationary, and then every second you're going to add another 100, okay. Every second, another 100. All right, and the 100 reduces to 5. You're going to have to plow through. You're going to hit 5 for every 100. It's the average. All right, and so it's kind of just, you're saying this, you're trying to predict, well, what's the, what do I have to do to get to point B, okay, the most efficiently? I have to defeat that, the coming in part. And the best way to do that is with velocity. Now, but I have to use fuel to get velocity. So The scenario is that the simple truth is, if I use enough fuel to shoot me through fast, well, I don't want to go past point B, because then that's wasted fuel, right? I'm using extra fuel to go past point B, so that's not going to work. And anything short of getting to point B, that is, if I don't give enough impulse to get me to point B, that's not going to work either. Then I'm going to use more fuel, because I'm going to have to, I'm going to lose efficiency. That's sort of the Galilean thing that has to sort of be explained. You lose efficiency if you just keep doing the 1, 1, 1 thing. You want to do the 3, 1 thing. You want to do the 3 velocity and then the 1 velocity thing. 3 units of distance and then just 1. You want to make it more efficient. So there's a perfect velocity. There's a perfect amount of fuel you can use to get from point A to point B, and it just happens to be the same amount of fuel, okay, that this mechanism would push you if you just stood in it and let it push you. There's a velocity you'd reach at and when you hit the ground, that would be exactly the velocity you want to use to go back up against it, the most efficiency, because it's the amount of impulse that'll take you exactly to point B through that much force per second. All right, so the simple argument being made is that, yes, the slower I go, okay, I'm really doomed, because I'm going to keep getting all these 100s. So if I take 10 seconds to get to point B, obviously there's 1,000 dots, okay, and I'll have to interact with 50 of them. All right, so it would be 1,000. I don't need all that. And I'll have to hit 50. But if I take 1 second, then I'm only going to be, it's only the 5 dots, the 5 extra, okay, and that's all I have to deal with is 5 extra. So the faster I can get from point A to point B, the less work I'm going to have to, less counter force I'm going to have to apply, because I'm going to evade all of these extra bits that are going to go through this square of space. So it's a pretty simple argument. I don't know why it has to be argued in all these ways, but I'll do all the various analogies that you can place on this simulation, okay, of the reality. Now, like I said, I don't know what they think gravity is, so I can't, they don't think it's a moving force, essentially. They don't think it's a force that has any energy, even though it clearly gives things energy. So how can it be a non-moving, non-real force if it gives objects momentum and causes them to move in a direction? I mean, I don't really understand how that works. So that's where we are. So anyway, so the physicist Michael was attempting to say that it doesn't take more work if I do it slower. So, and he did it in this sideways way where he didn't measure the total amount of work done, that is the total counter force applied to lift an object. So the simple argument is, if I lift something really slowly, I'll have to deal with a whole bunch, 100, 100, 100, a whole refilling of this force that's going to keep pushing. It's going to be 5 plus 5 plus 5 plus 5 plus 5 plus 5 that I have to keep overcoming. And then if I can lift it relatively quickly, I'm only going to have to go through a minimum amount of that force traveling through the space. It's a per second force. It's 9.8 meters per second on Earth. And it happens every second. There's a certain number, a certain amount of force that's applied per second. All right. And you can acquire velocity based on how much force hits you. Okay. Yeah, I don't know how you can't. I don't know how to make it much simpler. But anyway, we'll go through the other multiple ways you can view it. All right, back. So I was thinking probably have to go through something more elemental to really make this a more complete argument. So the scenario we're talking about is one where there is the ground, okay, and it So in the rocket example, okay, it's clear that if I shoot a rocket and I want to make it move, I have to have a constant force being applied to stay in the air. Okay, the rocket can't just stay in the air. So if I want to just make it stay in a foot off the ground, I'd have to apply a constant amount of force to overcome the fact that the bits of force are constantly coming down and giving me velocity in the opposite direction. And so the only way I can defeat that is I have to have a counter velocity that counters that force. So in Earth gravity, we're talking about 9.8 at most of these locations, and that has to be the counter force. So for every bit of 9.8 coming this way, I have to provide a 9.8 this way to stay here. That's it. So, and there's no hand holding it, right? There's no person. Okay, and we're not talking about me putting my hand on the rocket, okay, or a little stick holding the rocket in place. And then we don't need this thrust because then I can hold the rocket, right? So in place. And then the argument really is about, well, what's really holding the rocket then? Is it me or is it the ground? Because frankly, you can sort of understand that whatever I touch becomes part of me. Okay, and especially if I touch it in a substantial way, this now is my mass. If you weigh me, I weigh my weight plus this object because I'm suspending it. I'm stopping it from moving in gravity. I'm providing the counter force, and that means that I'm heavier. Okay, I've gained weight. So the weight of the rocket, okay, is now part of me. And the point is well, they're going to have some argument about whether I have to do work. Well, yeah, if I made me out of steel, then the transition of the weight is the same as the transition of the weight of my body, any piece of my body. It's work, but it's not work in the sense that all of the mass, all of the weight goes into the ground, and the ground does the pushing back up. And you feel that. So if I give you 100 pounds to hold, sitting in your chair, your ass will get tired sooner because it's more weight, right? So the more weight I put on you, the more work, in a sense, this transition point has to do. The more aggressive it's the application of its energy. And clearly, because we have arms with tendons and cartilage, we're going to keep doing something with our muscles to try to compensate for the stress that we're putting on them, because they want to bend and they want to do things, and we're going to stop them from doing that. And so we're going to have to apply a whole bunch of energy. So frankly, it's really not about the fact that with a human you don't have some smooth transition. Like, it's not a steel structure that goes down into the earth and has great rigidity, and therefore doesn't do much flexing, doesn't do anything to sort of waste energy. Okay, so but if it was made out of clay or plastic or something weak, you could understand that over time it would start to contract and bend and break. Okay, so there's lots of examples where you can show that, where the force isn't going to act immediately, but over time little tiny bits of the force are going to start being used to misshapen the thing you're using to hold it. Alright, so that's a little bit more complicated in an argument, but the simple argument is there's some examples where you're just trying to demonstrate that there is a difference, okay, between the rocket not being touched by anything, not being connected to the ground, not having any place for the energy to go except it. It has to provide any counterforce on its own. So, and then a human, say, standing on the ground, where, you know, the counterforce is basically the ground. The ground's doing the work. The force goes into the ground pushes the person back up. That's the simple truth. All right, and so the ground does most of the work, but clearly our body has to constantly carry, our upper body has to carry our arms and has to carry our head, and it has to manipulate, and we use a lot of energy to keep the gravity centered so we don't fall over. All right, so we are doing work. We're not doing work based on our mass. we're doing work on the inefficiency of our function. Okay, because clearly the efficiency would be we would just be a monopole, and we would just, you know, sit on the surface and have our mass up here, and all of the energy would be clearly easily going right into the ground, and there wouldn't be any fighting inefficient pulling up and pulling down and pulling up and pulling down to try to compensate for the gravity and do it poorly. And that's really all you're talking about, is a poor. So if this exhaust for this rocket wasn't consistent, let's say it couldn't do 9.8 perfectly, and it did 9.7 and 9.8 and 9.9, and so it was bouncing, you know, because it wasn't quite getting it right. Okay, it wasn't meeting the force efficiently. Well, obviously that would be motion, extra motion, and that extra motion would be expensive. So that would be waste. So the more perfect it can meet the gravity, the less energy it will use, and the more imperfectly it does it, going up, going down, jittering about, the more fuel it'll have to use to do exactly the same thing. And that's the subtlety of that argument. So all these examples will be examples where you go from, okay, standing on the ground. So I guess I could do one of the examples would be ice. So you have a patch of ice. Here's where the river goes strong, and there's thin ice there. And the argument is there's shore here, and then there's solid ice here, okay, and there's solid ice here, and then there's shore over here. And we're really just talking about, well, what does it take? What's going to happen if I want to go across this ice? What do I need to do, all right, to ensure that I don't fall through it? All right, and the simple argument is when I'm over here, all of the force will be going into something that won't break. And certainly over here, it won't break. The ground's not going to break. And my force is going into something solid. And now I'm going to go over this thin ice patch. Now, if I go over it slowly, it could be understood that my full weight now, the gravity will have plenty of time, okay, to give me my real weight, okay, and so I will be placing with each step that 150 pounds of pressure on the ice, and the fact is it can't resist that, and I will fall into the ice. But if I can slide across the ice at faster velocities, you know, maybe I can go a little bit, you know, slide a little bit, but it won't be quite enough, because the 9.8 per second, right, I'm cutting it into like a tenth of a second worth, you know, but it's still an amount. There's an amount, and that amount is going to get to me because I'm giving it enough time to make me heavy. But the faster I can go across the ice, the amount of pressure per square inch that I'll be placing on the ice will go down further and further and further. And certainly you could understand it as a total pressure. If I slide across really, really fast, the total pressure on the ice is going to be way down. And if I go across really slow, you can understand the total pressure on the ice is going to go way up. So you can understand that that's basically just telling you that the total force is time dependent. That really all that matters is how many of those little bits that are coming down that are giving me mass, how many of them do I let hit me? And the fewer I can have hit me as I go across the ice, the less weight I will have. And the slower I go, the more weight I have. Now, I can't have more than 150 pounds because that's how big my sail is for catching wind. I mean, I only have so much capacity to collect these things, so they're coming down at a rate. I have a surface. You could say my mass is a surface, and the mass is saying I can collect this many per second. That's how many the most I can collect. I can't collect any more than that. That's all I can collect, is that many per second. Which introduces a sort of draft, this drag argument, because you could argue that if I go up against the force, there's more force, but we kind of know that doesn't work for big objects. That only works for little objects. So that's another point to be made. But anyway, we won't bother with drag in this video. It sort of just demonstrates that Newton's first law isn't universal, because electrons and protons don't behave by the same rule as helium nucleus. The two things don't obey the same law, because one is one doesn't need a force, technically, to drag it to a halt. So in a gravitationally neutral environment, an electron moving is still going to stop moving. It's going to be dragged to a halt. It can't travel through empty space like a thrown wrench can. So it's different. So it's not exactly a universal law. It's universal for all matter that contains atomic nucleuses, but it isn't for the elemental particles. All right, it's technical arguments. Whether there's any point making technical arguments to the existing audience. Anyway, all right, so it's just clear that yes, you're going to fall through the ice if you allow gravity enough time, okay, to give you more mass, more weight. Okay, you can't give you more mass, it can give you more weight. Okay, it can apply force to your mass, and there's a slow speed where you'll gain the total amount you can collect from gravity. So going really, really slower and slower isn't going to make any difference. You're going to fall through the ice, right? So the going much, much slower isn't going to change anything. But going faster, that is defeating the per second force, the force that's happening per a unit of time, you can defeat the force by defeating the fact that it needs time to affect you. And if you can defeat how much time it has to push you into the ground, then you can defeat it forcing you to drown in the freezing water. So yes, you can just slide across the ice at a certain minimum speed will create the fact where you can make it crack, you can make it make noises, but you'll get across. And then the faster you go across, the less the ice even knows you were there. All right. I mean, that's so simple. I mean, so obvious. So we'll move on. So there's a thing to understand. Anytime something touches something else in these environments, yes, those things will now take away the energy. They'll now have to account for it. They're going to be part of the question. And so on all these earthly things, you have to understand that when you are, in fact, in contact with the earth, you can't collect any extra velocity because all of the force goes right into the earth. So you are just a conduit. You're just a piece of, you're an electrical wire, and you're just conveying the electricity. You're not doing anything with it. So you're essentially just pushing the force into the ground, and the ground's doing the work of pushing back. You don't have to. All right. And that's different than when you're responsible for fighting the gravity. All right. Alright, so let's do the light example, photons. And the interesting thing about photons, is this, the inverse square law. So right here, I'm showing you the inverse. My hand is this big. I'm going to cut the distance in half, and you can sort of see my hand is now quite huge. It's not twice as big, it's 4 times as big. That's the inverse square law. All right, and light does that. Okay, a light bulb, the closer you get to it, the amount of photons hitting you doesn't just double. So you go half as close to the light bulb, you're not getting hit with twice as many photons, you're getting hit with 4 times as many photons. So it works exactly like gravity. So all you can do, you can sort of think of a light bulb in reverse, and that's essentially gravity. It's some invisible stuff. The photons are invisible until they crash into your eye. You can't see them as they're traveling, just like gravity, you can't see them. Your body can detect them, so you know they're happening. So there's a very good analogy. It's both forces are moving the speed of light. Okay, the speed of light is relevant to how the gravity is transmitted. Gravitational waves, move at the speed of light. If there are such things, so it's just it's a very good analogy to the function of gravity in the sense that it has the same functioning rules. It behaves exactly the same essentially. So it's a perfectly legitimate way to understand what you're talking about. So the idea would be is that the ground, we could say, is when you're in a house and you're protected from the photons. You can't be moved by them. You can't be affected by them. And that's the same as when you're standing on the ground. You really can't in any way move. You can't collect the force. So we're just talking about when you're able to collect the force and get motion or momentum from the force. And so that's why these examples always have a point A, okay, and a point B, okay, a circumstance A and B, you could say, but it's also just duplicating a distance, all right, because the argument is that distance doesn't matter, speed matters. It's not about how far you're traveling. So if I was to go through a field of photons, okay, and I have my little reflector out and I'm going to get some suntan, and I'm going to go from one house to the other house, okay, the covered area and the covered area. And so we're just going to say the photons are essentially just as I described the gravity. I mean, it's just these little elements, and they're coming at a rate, okay, so you have a rate of photons that are constantly streaming through this area. And so per second you could measure the volume of photons, and it's always the same volume per second if the sky is clear and all that stuff. So it's a blue sky, the sun is perfectly happy, it's producing the same number of photons, and there's generally speaking the same number on average going through here every second. There's a certain number of photons. And the simple argument again is it's not about this distance, it's about how much time I spend in the field will decide how many photons I collect. And if the photons were momentum, they are technically, but they're not very much, then I would gain motion, you know. And if this was if I could float in space, they would be moving me eventually. They would give me a momentum, and I start going faster and faster as I gain more and more of them as a percentage of my mass. So the more of them I gain as a percentage of my mass, the faster and faster I will go. All right, so anyway, so the simple argument is that if I go from point A to point B really fast, if I go really fast, 1,000 miles an hour, I'll only get hit by like 6 photons, and I'm not going to get any tan at all. And if I meander and take my time and take an hour to play around out here, then obviously I'm going to collect lots and lots of photons. I'm going to get lots and lots of tan. So it's really just about, again, the time I spend exposed to the force. So the force is constantly raining on me, okay, the rain analogy, constantly raining a differential. And again, you don't have to believe it's particles. You don't have to believe that it's little bits. You just have to believe that there is a flow. Now, even when Leonard Susskind teaches the most abstract relativity theory, he uses mock gravity as an example. So he uses a constant stream of water that's essentially just pushing everything. So it's these analogies have to be used. There's no way to evade using comparison to things that we do understand. And the simple argument is it is exactly like, okay? I mean, photons are so similar to what we would say gravity is in terms of it being discrete, invisible. Now, photons do just affect surfaces, so let's understand they hit surfaces and pound on surfaces, and the only argument about gravity is the surface it's hitting is the electrons and protons. It's not really hitting any part of you. It's hitting it's hitting your elemental mass. It's not hitting atoms. It's not hitting it's hitting elemental pieces of your atomic structure. And so if I put a single electron, okay, in the field, it would behave the same way in the sense that it's just going to collect based on its mass. And so, in gravity, I could just take the Earth as it's spinning around the sun, and I could just put another electron right outside the Earth, and it'll do the same orbit. It'll do the same thing if I give it the same velocity. All right, so it's a simple enough argument, okay? You go outside. The longer you're outside, the more light particles hit you, light waves, light whatevers hit you. And it's just a simple fact. If that's what's going to give you more or less velocity if there was velocity. So the only difference between light and gravity is gravity is giving you velocity where light's giving you a suntan. And the argument simply is the more time you're in the gravity, the more time you're in the sunlight, the more force, the more effect it's going to have on you. That's simple, because it's coming at 9.8 meters per second. It's a per second force, per 1 second. This is how much happens in 1 second. This isn't how much happens in 10 seconds or 40 seconds or 90 seconds. It's in 1 second. Explicitly 1 second. Why would you square 1 second, right? Does that make it? No, it doesn't make. Of course it doesn't make any sense. Why would I square a 1? Pointless exercise. That's the rate. Okay, not what they say. Every time you hear 9.8 per second squared, it's just a nonsense. This is the real formula. All right. We shall move on. An unfortunate glitch. Anyway, so let's try a different analogy, one I haven't used before. So we could use baseballs. Okay, so we have a gun that shoots baseballs. Okay, and it shoots them based on a rate. Okay, so it shoots whatever, 10, let's say, per second. All right, and so it just shoots the. So you could almost argue this could be the gun analogy also. So it covers a lot of different ways of making the point, okay, that there's a rate of something. All right, and the simple truth is that, let's say the baseballs don't come out perfectly even, and there's a field that they do pass through. So they just pass through this point A to point B field. There's a field where the baseballs travel through. Okay. And the fact is they're coming at a rate, all right, a constant rate. And the simple argument is like I said, I could freeze it. Okay, I could just stop time, and there would be a baseball here. Well, cool. A baseball here, a baseball here, a baseball here. All right, I could just calculate how, what's the odds of me having to hit a baseball, whether I like it or not. And we could just say that no matter what I do, there's always one baseball in this path. So I can't get from point A to point B without hitting at least one. All right, and now they're coming at this rate. So obviously the fact that they're keep coming through this area means that any extra now I've got a problem, because now it matters how fast I go through, because now there's a constant rate of them. So now I can figure out that, like a paint sprayer. Yeah, so this does paint spray too. Let's just say it's the paint spray analogy. The simple argument is the longer I dawdle in this field, the more paint that'll hit me, the more baseballs I'm going to get hit by. It's just obvious. And the faster I can get through the field, the less baseballs will hit me. It's kind of obvious. And if I was going against the field, the same sort of rules apply, in the sense that that they're always coming, and I'm going against that always coming force. And so the faster I can get from point A to point B, the gun, past the gun, the fewer baseballs it's likely I'm going to hit. So I could do the analogy as I'm going to run towards the guy shooting the bullets. Right? There's a guy with a machine gun. I'm going to run towards him. Now the faster I can run towards him, the fewer chance that I'm going to hit a baseball and get shot. And the slower I go, obviously there's a higher chance I'm going to get shot with a bullet. So it's just kind of obvious that the slower I go, the more force I'm going to have to deal with, the more bullets. The faster I can go, the less bullets I'll have to deal with. So let's just say I had a shield and I could deflect bullets. It's just sort of an argument that there's a point where, there's too many bullets and I can't deflect them and one of them gets me, kind of argument. So you can understand either way. If I'm going this way across the field, okay, speed matters. And if I'm going into the field, speed matters. The faster I can get through whatever's going to be in this field for the amount of time I'm traveling, the fewer number I can make this number, the fewer number of elements of this per second amount, the fewer seconds I allow, the less stuff I have to deal with. And the longer I extend the time I allow it to be 19.6 19.6 is a lot more baseballs than 9.8. And if I keep letting it grow, you know, the number of baseballs, yeah, obviously it's going to be more work for me to deflect or to avoid or to stop or to counter that force. So the faster I get to A, from A to B, the less work I'm going to have to do countering baseballs. And the slower I go, obviously the more work I'm going to have to do dealing with baseballs or paint. So the more paint gets on me, the slower, the longer I linger in the paint spray, the more paint is going to get on me. The more rain, if I'm meandering around, you know, in between two houses, instead of just going quickly, I just, you know, screw around having a cigarette. I'm going to get wet, really wet. So the slower I go, the wetter I get. The faster I go, the less wet I get. I mean, I really shouldn't have to make these arguments to adults. But apparently you do. All right, let's see if anything else is necessary. All right, I guess we'll just sum up. No point in doing rivers and wind. I mean, I could go through all of the applicable analogies, but there's an awful lot of them. I think the other important feature, I guess, to just say is that this just has to do with formulations of reality, okay? And this is the simple one they distorted, okay? It's this simple argument. And then they went a step further in the distortion when they put the squared on here and decided that they were going to say that the important thing is distance, you know, how far you travel or how high you go in gravity. So the applicable one is gravity. And so they say it's mass, okay, mass times gravity, which makes sense. I guess this one's done. All right. It's always something. All right, I think if I press hard enough, this one will work. Yes, MGH. So they said this is the magical formula that you know, mass times the gravitational constant times, so the times the rate times your height. That your height is going to tell you how much work you're going to do, and that's all that matters is your height. When clearly the argument is that when you're falling in gravity, you're doing the Galilean thing. You do this in 1 unit of time, you get 9.8, and then you do this whole section in 1 unit of time, 1 unit of time, 1 second, one per second. 1 unit of time is all I need to say. And so you're doing 3, okay? Same time, and you're still getting the same 9.8, because down here you're going to have 19.6 as a total. So you only gain 9.8 in this long distance. Clearly, distance isn't what's controlling, okay? It's mgt. The time is what tells you how much force you'll have to counter or how much force you will collect, okay? And that's the key component. So they've turned it, because they did this MGH thing, then they end up counting each one of these units of distance and say, because you got 9.8 in this unit of distance, somehow you got 9.8, 9.8, 9.8. And even though your velocity is still only 19.6, they're going to claim it's as if you collected 4 times the force, when you were only in the force 2 seconds, 2 units of time. So it's only 2 units of time, and yet they're saying you square this, so you end up saying this is, you know, twice as much energy as it would be if they didn't, you know, screw it up with their wrong formula by counting this wrong. This is 1 unit. This is 1 unit. That's all you got. 2 units of energy, 2 units of time, 2 units of energy. That's all that's there. And that velocity number is telling you that pretty clearly, because that's mv. That's proving, that's showing you that's the same momentum. You know, that the momentum doubled because you're going twice the speed. And that's what happens. You go 4 times the height, you double your weight. Now that's a test I've actually done, but you know, I haven't done it, you know, clinically perfect. Did it with kind of a cheap, cruddy little scale. But, you know, you can do it. It's a doable experiment. They could do it clinically, but they don't. But you just take an object, and I found if you drop it from 1 centimeter, that will double its weight. and 1 centimeter means 1 mile an hour. So 1 mile an hour doubles its weight. 1 mile an hour of impulse. Okay. For 1 centimeter. And you go 4 centimeters, and that doubles that. And it, you just keep doing this doubling thing by going 4 times higher. And so that's all you're getting out of it, is double the velocity, double the momentum, double the weight. So I didn't really want to get into all those arguments, but that's how this all goes wrong. So they're going to insist that if I drop 1 pound from 4 feet, it's going to create the same energy by their formula as me dropping 4 pounds from 1 foot. When no, it's not. This is only going to have half the energy. 1 times 4 isn't the same as 1 times 4 is 1 times 2. Okay, 2 units of velocity isn't going to be the same momentum. So 2v and 1 pound at 2v isn't the same as 4 pounds at 1v. Not the same at all. Not the same momentum, and it's a momentum universe. So this is Newton. Okay, let's understand. Newton never said 9.8 meters per second squared. He didn't say per seconds per seconds. He didn't do any of that nonsense. And they slander Newton with the fact that he did say some kind of crap like that when he didn't do it. And he didn't do this MGH thing. He didn't do this. He didn't do any of that crap. That's all stuff they invented in the 1800s. Okay, so none of this is Newton's physics. Their physics isn't Newton's physics. And yet they'll talk about Newton and say, that Newton's relevant, and when they totally diss his entire worldview. They've completely perverted it. It's like as offensive as somebody walking into, this Mecca, okay, and then claiming the Ayatollah is really a Catholic. Just imagine how long you would live if you did that. Yeah. Or if you accuse the Pope of being a Muslim. Just think of the riots that would take place. But no one cares. They slander the hell out of Newton. Nah, it's okay. Who's he? He shouldn't be respected. He only devoted his life to science. I mean, why would scientists respect somebody who devoted his life to finding the truth? What's the big deal? Yeah, we should slander the fuck out of those people. Just piss on your heroes. I mean, just absolutely, just disgrace them in any way possible. Why don't you just dig him up and put his bones on display in some freak show? Show that you really love the guy. All right, anyway, it's just too pathetic. All right, so I guess we're done and such. I think that's enough of a commentary. It's just all based on, like I said, they just pervert everything that was the rational physics discovered by Galileo, Descartes, and Newton, and they just perverted it all into mush. Useless mush. And it is useless. It really isn't doing the world any good. MV squared hasn't done anything, hasn't invented anything, didn't improve anything. I don't think anybody could come up with a single example how your smartphone or any of your technology was at all created by MV squared. It hasn't done this planet any good at all. And the very fact that NASA just ignores it. I mean, NASA just pretends it doesn't exist. It's just so ironic and funny. But all of that nuclear accelerator stuff, all the Hadron Collider and all that, it's all way up its butt. And so all the answers it gets are all wrong. Okay, because, it's got all that MV squared stuff in it. Like I said, they couldn't even calculate the correct mass of an electron because they used MV squared. And so they got the wrong answer. And they've had the wrong answer for a long time, and that's why they got everything wrong. So, but I'll get to that in another video where I'll explain the difference between a neutron in an atom and a hydrogen atom. Okay, so till that time, or some other time, till the next time. That's what's probably the most useful thing to say. But yeah, everybody just trying to look, you don't have to believe, okay, that time is the most important thing. but you have to concede it is a time-dependent force. Okay, you want to say distance is really important, and I love distance, and distance is my friend. Okay, go ahead to an extent, but time is the thing in control. Okay, it's a time-dependent force. There's really no conversation, frankly, if you're going to deny the time dependency. The fact that this is a rate. This 9.8 thing is a rate. It's a rate of change. It's a rate of disproportion between what's above you and what's below you. It's a real thing, and you can't deny it's completely time controlled. The more time it has, the more force it's going to apply. And to deny that is just to be too belligerently stupid. So maybe you can accept it and say, well, there's a catch, or, well, blah, 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 make up some excuse. But you can't deny the actual fact that it's a per second, 1 second force. This 9.8 doesn't mean anything without this 1. Without the 1, their 9.8 doesn't mean anything. It's irrelevant. It's stupid. It's useless. The 1, if I put a 2 here, this number has to change to 19.6. It's incredibly important that you understand it's 1 second is 9.8. Not 10 seconds, not squared seconds, not any other kind of seconds. It's 1 second. And if you're denying that, you're just too stupid, frankly. You're not worth my time.